We're down to our last two series tests, and this is number 9. It's the ratio test, and it says for a series, find the limit as n approaches infinity of an plus 1 over an, and notice it is the absolute value. So after you take this limit and you get your answer, which I just called L, you can determine if it converges by looking at what the limit is. If the limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. And if L is equal to 1, then the ratio test is inconclusive. So let me go ahead and tell you, as far as our test is concerned, if it specifically says what does the ratio test find, then inconclusive is a good answer. That's fine. But if it just gives you a series and says determine if it converges or diverges, if you choose the ratio test and get inconclusive, you need to pick something else. So if it specifies ratio test, you can just put inconclusive. If it doesn't, then you need to do whatever it takes to figure out converge or diverge. So let me explain a little bit about this an plus 1 and the an. Basically what's going to happen is you're going to take the sequence and you're going to make a fraction. You're going to put the original sequence on the bottom, and you're going to change all the n's to n plus 1 to make a new sequence on top. So I think the simplest way to do that and explain that is just to show you an example. So here's one where the ratio test would be helpful. The ratio test is typically helpful when you either see a factorial, which you have here, or if you just have a lot of mixture of different types of functions. Like if you see exponential mixed with factorial, or exponential mixed with polynomial and that kind of thing, that is a good sign that you want to use the ratio test. So here's how this works. You set up the limit as n approaches infinity of the absolute value, and then you set up a fraction. You put the original on the bottom, and on top you just change all the n's to n plus 1. So I get 2 to the n plus 1 and n plus 1 factorial. So again, original goes on the bottom. On top, you rewrite it where all the n's change to n plus 1. Now I've got a fraction over a fraction, so I will multiply by the reciprocal. Now the 2 to the n and the 2 to the n plus 1 will cancel out, leaving just 1 2 on top, because there's one more 2 on top than there was on the bottom. Okay, if you remember back when we expanded factorials, n plus 1 factorial could be written as n factorial times n plus 1, because that would give you the numbers 1 through n and n plus 1, which is the same as doing 1 through n plus 1. So that means n factorial will cancel out, and it just leaves you with 2 over n plus 1. Now if you take the limit of 2 over n plus 1, you're going to get 0. And according to the ratio test, if your limit is less than 1, which 0 obviously is, then your series converges. Okay, next example. This is the one I was mentioning where you have a mixture of things. We have exponentials, that's the 2 to the n plus 1 and the 3 to the n, mixed with a polynomial n squared. So we do the limit. As n approaches infinity, we put the original on the bottom, and then on top we change all the n's to n plus 1. So n plus 1 squared, 2 to the n plus 2 over 3 to the n. Okay, because really what happened right here is we changed n to n plus 1, and then we also had the plus 1 that was already there, so that gave us the plus 2. Fraction over a fraction means we have to multiply by the reciprocal. Oh, sorry, I forgot a plus 1 over 3. There we go. That's what it should be. 3 to the n over n squared times 2 to the n plus 1. Okay, the 2 to the n's, we have one more on top that'll be left over. The 3's will have one left on the bottom, because there's more 3's on the, there's one more 3 on the bottom, and there's one more 2 on the top. Now we can't do anything about the n plus 1 squared and the n squared. Polynomials, unless they're identical, like if they're both n squared, won't cancel out. So we're left with the limit as n approaches infinity of 2 times n plus 1 squared over 3 times n squared. Now the powers are the same, n squared and n squared, so the limit would simply be their coefficients, which would be 2/3. So again, since this limit is less than 1, we would find that the series converges. Now we have this one, n to the n over n factorial. Just so you know, n raised to the n is pretty much the most powerful type function you'll ever run across. It's even faster than n factorial. So again, since we see a factorial, that's a good hint to use the ratio test. We put the original on the bottom, and on top we change all the n's to n plus 1. Okay, then we have a fraction over a fraction, so we multiply by the reciprocal. Now the n's to the n and the n to the n plus 1 to the n plus 1 we can't really do anything with. In other words, this piece and this piece we can't really do anything about. But, just like before, n plus 1 factorial can be rewritten as n factorial times n plus 1. So now a couple things will cancel for us. Sorry, I need to include my absolute value here. N factorial cancels, and 1 n plus 1 will cancel. So just 1 n plus 1, which still leaves us with n plus 1 to the n. So we have n plus 1 to the n over n to the n. And if you do that limit in your calculator, just use the table and see what happens as you get bigger and bigger, you're going to find that the answer is actually e, which is 2.71, somewhere in that neighborhood. That's bigger than 1, and according to the ratio test, if you are bigger than 1, then you are going to diverge. Which, if you listen closely to what I said at the beginning, would make sense. If n raised to the n is faster than n factorial, then we should know by the nth term test that we would diverge, because the top's moving faster than the bottom, so the limit right away would have been infinity. Okay, final example. We have negative 1 to the n times the square root of n over n plus 1. Okay, you can still use your old rules here. In fact, if this was on a test, I'd probably encourage you to do the alternating series test. But just for the sake of some practice, I'm going to use this one with the ratio test. And there's two specific reasons why that I'll explain as we go. The first reason is I want to make sure you know that because of the absolute value signs, you can essentially just cancel out the negative 1 to the n's. So again, I put the original on the bottom, and I change all the n's to n plus 1 on top. So we get that. Okay, well, we have to multiply by the reciprocal now. Okay, well, if you notice, the negative 1's would all cancel out except for 1, and we're doing absolute value. So absolute value of negative 1 is just going to be positive 1. So really, you can ignore those from the get-go. If you want to just ignore these, that would be completely fine with the ratio test. Now, what's left over looks something like this: square root of n plus 1 times n plus 1 over n plus 2 times the square root of n. And if you take the limit of that, you just get 1. So the two reasons I did this example, first, is to show you that the absolute value will just get rid of the negative 1 to the n's. And second is that we get 1. And if you get 1, that tells you that the ratio test is inconclusive. So again, on a test or a quiz, if they ask you to use the ratio test, it's completely fine to just answer inconclusive if you get 1 as your limit. But if they just ask you to find if it converges or diverges, you need to try something else. In this case, I would try the alternating series test, and you would actually find that this converges.